Hello everyone, welcome to Spark Study. We have studied about the Bode plot and we also done one problem regarding the Bode plot, that means how to draw the Bode plot. So that is not enough. Drawing the Bode plot is not enough, but it is the pre-part stage to solve some more concept, some more problem also. So the most important terms what we are going to use or we are using in Bode plot will be discussed now. Then after we'll do one problem also. So the first point will be the corner frequency. That is a more important thing. And I told you the magnitude plot of Bode plot is to be joined by a straight line or using scale. So that is not actually the correct thing, but we approximate it make a straight line. So this is a small curved line. The curve will be around 3 decibel 3 dB gap, but that is not enough. That's why we are approximated by a straight line. So the magnitude plot can be approximated by a asymptotic straight lines, and the frequency corresponding to the meeting point of asymptotes are called as the frequency. So we have a straight line, then we have another straight line. When both straight lines join together, the point is called corner frequency. Or you can say the slope of the magnitude plot changes at every corner frequency. What I have already told you. That means at corner frequency the slope changes. So this is all about the corner frequency. Then important thing is phase crossover frequency. The here phase stands for its angle. Okay, so that means at what angle at what frequency the angle crosses the phase line, or like that some concept. So it was denoted by omega pc. Let us study about that. The frequency, what is a phase crossover frequency? It is a frequency in radian per second at which phase of OLTF or angle of OLTF is 180 degree. Remember this thing, it is a frequency at which the phase of OLTF is 180 degree. That means you take the OLTF and put the value of omega. So at what omega this transfer function becomes 180 degree. I mean the angle of the transfer function becomes 180 degree. That is called phase crossover frequency. Similarly, we have another term called gain crossover frequency, and it was denoted by omega GC. Okay, so the frequency at which magnitude or the gain both are same na, of OLTF equals 1. So when you convert 1 into decibel, 20 log 1 equal to 0 dB. That means either one is correct. So frequency at which the gain is 1 or the gain is 0 dB. That is called the gain crossover frequency. So these things are important. The corner frequency, the crossover frequency, that is gain crossover frequency and phase crossover frequency. So from these two kind of frequency, that is gain crossover frequency and phase crossover frequency, we also get to more term that is called gain margin and phase margin, right? So before studying gain margin, we should know what about the margins. Okay, so let's say this is the area where the system in it at each and every point that my system is stable. Okay, and we have another area red in red, so that is unstable region. Okay, so the white line in between these two is the margin line. Okay, let's say my owner or my company head asks me to design a system which is left to the blue line. Okay, that means we have my system should be stable, but we will work with this area up to this area. Okay, that means it was asking ki the system can be operated in this area also, but for now, for regular condition, let us work in this area, because if some fault occurs, the thing will travel to this side, and we also have some margin to make my system stable. That means after this margin, this is called margin. Okay, so after this margin, my system, if you move forward beyond the margin, the systems becomes unstable. So gain margin or phase margin, I don't care. So if you go for gain margin, it is the value beyond which the system becomes unstable. Likewise, for phase margin also, it is the margin or value beyond which the system becomes unstable. So this is the operating area or stable area, but it was not in used. It was stored for some future purpose. Okay, so if you go for definition, the gain margin Ks or simply K is defined as the value by which gain of the system has to be increased. That means here we have increased the gain from this line to this line. Okay, so we can say the system, the gain of the system has to be increased to drive the system to the verge of instability. Okay, उसका मतलब कि हम हमारा सिस्टम का गेन उतना बढ़ा सकते हैं, उसके बाद मेरा सिस्टम अनस्टेबल हो जाएगा. So it is given by the reciprocal of the magnitude of the open loop transfer function. That means it is a formula. So at phase crossover frequency, that is important. For gain margin, we need to consider about the phase crossover frequency, and for phase margin, we need to consider about the gain crossover frequency. So let me repeat this line. It is given by the reciprocal of magnitude of the open loop transfer function at phase crossover frequency. मतलब जो भी तुमको ट्रांसफर फंक्शन दिया होगा, ट्रांसफर फंक्शन से हम लोग मैग्नीट्यूड निकाल लेते हैं या फिर फेज भी निकाल लेते हैं. तो उसका मैग्नीट्यूड निकालने के बाद जो ट्रांसफर फंक्शन बचेगा, उसका रेसिप्रोकल लेके उसका ओमेगा के जगह में अगर ओमेगा पी सी तुम पुट करोगे, तो जो के निकलेगा और जो वैल्यू निकलेगा, दैट इज कॉल्ड योर गेन मार्जिन. सो व्हेन एक्सप्रेस इन डेसिबल, अगर इसको डेसिबल में हम एक्सप्रेस करेंगे, it is given by the negative of dB magnitude of G of j omega at phase crossover frequency. So we can write the gain margin Kg equal to the reciprocal of the magnitude of G of j omega, but here omega is equal to phase crossover frequency. And if you represent it in decibel, we can write minus 20 log of this value. Why minus? Minus means it can be go. Okay, so this is that is why this is minus. when it take this 20 मतलब कि 20 हम अगर ऐड करेंगे तो कोई फर्क नहीं पड़ेगा, ये तो माइनस होकर रखा है पहले से. ठीक है, अब अगर यू कैन सी इफ दिस इज सम वैल्यू, you are taking minus 20 up to here, you are taking minus, then we are working, that is why you use minus over here. Simple, just remember that this is the value. How to find out the gain margin in dB? Just multiply 20 log this value. Okay, and one more point is that key, if to find gain margin, you always focus on phase crossover frequency, and this gain margin, phase crossover frequency, gain crossover frequency, this will come from the Bode plot. Similarly, if you go for phase margin, it says that the phase margin or gamma is that amount of additional phase lag at the margin or at the gain crossover frequency. Here term is gain crossover frequency, right? So for phase margin, it is gain crossover frequency, it is omega gc, required to bring the system to the verge of instability. So it is given by 180 degree plus phi gc. Okay, we need to find out the phi gc. What is the phi value at omega gc? That means what is the phase at omega gc? That means at gain crossover frequency, what is the angle or what is the phase? Where omega gc or phi gc is the phase of g of j omega at gain crossover frequency. If you write with the formula, you can write phase margin equal to gamma, which is nothing but 180 degree plus phi gc. Here gamma is in a degree, not in radian per second, because we found the angle, that is we found the angle with this frequency. Okay, once you do the problem, we can understand easily. So we can say omega gc equal to angle at omega equal to omega gc. I repeat, for finding phase margin, you go for gain crossover frequency, and for finding a gain margin, you go for phase crossover frequency. Just I mean the um, cross multiplication type. Okay, so what are the advantages of the Bode plot? So we have done the Bode plot, we studied some concept of Bode plot, and many more things. Why, what is the advantage of that plot? So let us study all these advantages one by one. First will be the magnitude are expressed in dB. Okay, so a simple procedure is available to add the magnitude for each term one by one. I told you. So all the multiplication will be converted into addition at this point saying. Second, the approximate Bode plot can be quickly sketched and the correction can be made at corner frequency to get the exact plot. I told you what we are drawing or what we have done, it's approximate. That means for your semester level or your gate level also will get this approximate one. But if they ask for exact one, so what you do, in the corner, I mean at the corner frequency, you just add 3 decibel. Okay, just carve it out, so you will get exact one. Everything remains same except that. Third one will be the frequency domain specification can be easily determined, and the fourth one will be the Bode plot can be used to analyze both open loop and closed loop transfer function. Okay, so the previously let's say the question will be, let me try to use the previous question and do some other work. The sketch the Bode plot for a given transfer function and find the value of k at 5 radian per second. See, the previous question what we have solved is this thing. Sketch the Bode plot for a given transfer function, and the transfer function is given by g of s equal to s square by 1 plus 0.2s into 1 plus 0.02s. What I have modified here, I have I have multiplied a k in the numerator, and I asked what is the value of k if my frequency is 5 radian per second. Okay, so the question is, it look like simpler, but some very small concept is there, we need to find it out. Acha. So we can if you go further, this is our plot, right? Phase plot, and we have found the gain plot also like this. Okay, so for the transfer function, when k value is not given, I mean k value equal to 1 in that case. So now the question asks, find the value of k at exactly at omega equal to 5 radian per second. So the at 5 radian per second, if you put a vertical line at 5 radian per second, we can see clearly that the value of gain will be around 28 decibel. Okay, so if you first plot a straight line parallel to the y-axis or parallel to the gain axis exactly at 5 radian per second, which should be cross the I mean gain line. Then at that point you take a horizontal line which will cross the gain scale in dB. So we can find it easily that at 5 radian per second the gain is 28 dB. That is positive. Now one question I can ask you, uh, the previous plot, I mean here the previous plot we have used k equal to 1, right? But here k is some value, some 28 dB. That means when k equal to 1, if you see uh, if you see this transfer function, here some k into s term is there. I mean here k just multiplied with the numerator. Let me take k equal to 1. When k becomes 1, I'll get this transfer function. That means if you can write 20 log k equal to 20 log 1 equal to 0 dB. उसका मतलब ये है कि अगर मैं k का वैल्यू 1 लूँ, that means my the if you take my k value 1, then the dB value or decibel value or logarithmic value of 20 log 1 equal to 0 dB. If you plot this thing in 0 dB, you can see this is the line, red line. Okay, that means this red line corresponds to k equal to 0 dB. Okay, or k equal to 1. In normal scale, at k equal to 1, this line corresponds, or you can say at 0 dB, this is the k line, or this is the k point. So what is the frequency over here? You can see this line crosses here, and if you go straight then build down, so you can see it is around 1, right, at 1 radian per second. So you can say when when k becomes 1 or 0 dB, the frequency becomes 1 radian per second. But it was asking what is the value of k at 5 radian per second. Now we found that at 1 radian per second k equal to 0 dB. Then what at 5 radians per second we also found that k equal to what, 28 dB. That means we can see this is the gain when you travel from 0 to 28. Okay, in log scale, when you travel from here to here, this is called gain na. K equal to 1 do not affect the transfer function, but k equal to some value will affect transfer function. That means this much is the gain. Okay, if this much is the gain, we can say log of this minus log of this, or I can say 28 decibel minus 0 decibel. तो पहले ये था, उसके बाद ये हुआ ना. सो यहाँ से अगर 28 माइनस हम कर देंगे तो हमको क्या मिलेगा, गेन मिलेगा. दिस माइनस 0 इज कॉल्ड दैट इज द रेंज. तो यहाँ पे 28 था, 28 को क्या करेंगे तो 0 मिलेगा. दैट मीन्स 28 से -20 ऐड कर देंगे. अगर 28 को -20 ऐड कर देंगे तब हमको 0 मिलेगा. तो हमको ये समझ में आ गया कि ये जो डिस्टेंस है यहाँ पे हमारा गेन -20 dB हमको ऐड करना पड़ेगा. देखो ध्यान रखो, तुम कंफ्यूज हो रहे हो कि प्लस क्यों, मतलब 28 माइनस 0 इक्वल टू 28. Why you taken -28? I have not taken -28. What I did is from this line I have subtracted 28 to get this line. My aim is to, ultimate aim is to get this line because I want to make the k equal to 1. So that what happen when 20 log k equal to -20 dB. And if you solve for k, log k is equal to -28 by 20 and k equal to 0.0398. This is the k value. Okay, you understood? Okay, I repeat again. If you are not able to understand, let me repeat again here. It was asking for transfer function in the numerator k, what will be the value of k when your omega equal to 5 radian per second. So after drawing my Bode plot, I have taken a straight line exactly at 5 radian per second, which will meet the gain axis, and then after we have taken a straight line to get the value of gain exactly for corresponding to 5 radian per second. And I have found that for 5 radian per second my gain will be 28 dB. Okay, so the question what asked to find that value of k, we do not have the direct formula, so we need to analyze like the geometry, we need to analyze. सो के का कुछ वैल्यू 20 लॉग, यहाँ पे तो हम ऐसे बोल सकते हैं ना, करस्पॉन्डिंग टू 5 रेडियन पर सेकेंड, दिस वैल्यू वी कैन से 20 लॉग के इक्वल टू 28. यस और नो? सिमिलरली तो ये तो गेन हुआ ना. ये एक्चुअली जब के का वैल्यू 1 होगा तो मतलब 0 dB होगा, तो ये वाला लाइन होगा. यहाँ से कुछ चेंज करके यहाँ तक हम पहुँच गए, मतलब तो यहाँ से चेंज करके यहाँ तक पहुँच गए. उसका मतलब अगर यहाँ से सब्ट्रैक्ट कर देंगे तो यहाँ तक पहुँच जाएगा ना. तो ये तो गेन हुआ ना, इसलिए मैंने क्या किया, ये 28 था. अच्छा, कभी ऐसा भी हो सकता है कि अगर तुमको पूछा गया व्हाट इज द वैल्यू ऑफ के व्हेन के इज इक्वल टू 0.5, 0.5 मतलब यहाँ आएगा ये वाला अराउंड -12 और -13. तो वहाँ से क्या, फिर यहाँ पे 0, सो -12 प्लस 12 इक्वल टू 0. यहाँ पे 28 -28 इक्वल टू 0, यहाँ पे -12 होगा, -12 प्लस 12 इक्वल टू 0. सो जो भी वैल्यू है उसके साथ हम क्या करेंगे ताकि हम 0 dB में पहुँच जाएंगे, that is equal to 20 log k. Okay, so this value becomes 20 log k equal to this much, and we have found out the k value. Remember, we have drawn the Bode plot. It is approximate Bode plot. What the is mean? We have just taken a straight line from here to here, then here to here, then here to here. That this is not actual. So what happened? This has to be bent somewhere here in with respect to corner frequency. So in each corner frequency, we have a smooth transition. Okay, that is why if you plot the exact exact Bode plot, the phase the gain plot will be little bit bend over the corner frequency. Everything remains same except the bend. That is why if you want to find the exact value, this is the approximate value of k. If you want to find the exact value of k, what you need to do, instead of minus 28, you have to add 3 dB. So it becomes 20 minus 25 dB. So 20 log k equal to minus 25 dB. So that's the point. So we can take the frequency omega equal to 5 radian per second is the kernel frequency. Hence, in the exact plot, the dB gain at omega equal to 5 radian per second will be 3 decibel less than the actual plot. Remember that addition of 3 dB will be applicable if the frequency is kernel frequency. That means if they ask what is the value of k at this point is not a kernel frequency, so you just add some 28 in minus 28. But if you ask for kernel frequency here or exactly somewhere here 50 or 100, those are the corner frequency, then you have to add 3 dB. Therefore, for exact plot, the 20 log k will be contribute a gain of 25 dB minus 25 dB, which is equal to minus 28 plus 3. So after that, we find the value of k. I'll get 0.0562. So it was asking for exactly at 5 radian per second. So you'll get a deviation of 0. You can see here the deviation will be 0.0398 and here 0.0562. This is the deviation. If it is not, if they ask k value not at the corner frequency, then the deviation will be 0 because we will not going to add the this 3 dB. Okay, so anyway, this thing is not in your syllabus. So if it could becomes in the competitive exam. So thank you for this concept. Hope you are enjoying the video. If you enjoy the video, please don't forget to like, share and subscribe to Splash channel. Thank you very much.